Okay, so in this part of the lectures, we will discuss the cache policies, and to illustrate this, we'll assume that we have uh, the CPU, which is the MIPS here, okay, and the CPU issues an address of a 32-bit, okay, 32-bit. Now, this address will start to partition it based on the policies, because the policies will dictate how I partition the address and will help me do some determinations, especially in the placement policies. So now this is a 32-bit, and let's assume, so this is my cache here. Let's assume certain assumption of the cache. Let me assume so my address size is 32-bit. Let's assume my cache size is for example 128 bytes. Okay, and let's assume that my block size is for instance 16 bytes. Okay, and therefore if I want to there is one important cache specification metric, which is how many blocks I have in the cache. And this is simply by we divide the size of the cache in terms of number of bytes over the size of the block, and we have 8 blocks. So this cache has 8 blocks. Okay, all right. Now, with that said, we will say the following: that this address which I used right here, okay, let me just do an erase here. Eraser. Okay, so let's erase this, and this address space now with the address, we will now start to partition it into the following fields. We will have what we will call a block offset, and the block offset is how many bits I need to designate a byte inside the block. So the number of bits in block offset, number of bits in the block offset equals log of 2 of how many bytes in the block, which is equal 4. So 4 bits, those are 4 bits. Okay, 4 bits will be used to identify the byte within the block. Okay, so now what we need to do is we need to continue with this partitioning the address, because it has to do with my policy. So this is the 32-bit address. Okay, so we have two other fields. We have the index and we have the tag. Basically, the index identify for me the set where the set in the cache where block lives, and that takes me to the cache policies. Now we'll talk about cache policies. Cache policy can be direct, and it can be k-way, where in this example we'll use k as equals 2 and as an example, so we'll talk about two-way, for example. And the third policy is fully associative. Fully associative. Okay. Now, so I understand in the cache. Let's see if we draw the cache with with this color here. Okay. I understand the cache has how many blocks? We identify this as 8 blocks. So here in the direct policy, whoops, I should make it a little smaller. Yeah, so I can get things sneaked in. Okay, so here in the direct cache, see if I can use this. See. Okay, so I need here lines really. 1, 2, 3, and probably 4. So I need to delete this so I organize myself a little better. Okay, so let's say K is we'll use two-way here. Okay, so we'll use two-way. Okay, as an example, and now we'll have this as one line here. 1, 2, 3, 4. Okay, now so let's draw those caches. So in the direct policy, so here is the cache. It contains 8 blocks. In the cache, we have the 8 block. Every block of them is a set by itself. So here is set 0, set 1, set 2, all the way to set 7. And therefore, while we know that a number of blocks equals 8 in this cache, we have computed this earlier. Okay, every set has one block. So the set size, every set has one block. Every set of those has one block. This is just one block, and therefore we have 8 sets, which contains 8 blocks. Okay, and so how many number of sets, by the way? Well, I have number of blocks 8 divide by what is the size of the set, one block. It means I need 8 sets, and this is exactly what I have. This is 8 sets. And finally, now the index, remember that we talked about the index here. We will use the index to indicate the set number. So how many bits I need in the index? So index bits, it is log of 2 to this, which is equals 3. Okay, which is equal 3 bits. Okay, let's talk about the fully associative. The fully associative assumes, so here I have 8 blocks, okay, but it assumes that the entire cache is one gigantic set, one set. It is set 0. You can call it set 0 if you want. And in this case, yeah, we still have 8 blocks. That didn't change. The number of blocks, 8 blocks. But the set size here, I have 8 blocks per set. That's the set size. The set size for the fully associative is 8 blocks per set. So how many number of sets I have? How many number of sets I have? Well, 8 blocks in the cache divide by the set size, which is 8. It means I have one set, which is true. I just have one set. Well, how many number of index bits I need to designate? Log of 2 of 1, which is this one here, equals 0. And therefore, the fully associative cache does not have index bits. No index bit whatsoever, because we don't need to. The entire cache is one set. So the index bits are used to indicate the set number. Okay, and since I have only one set, I don't need index. So that's why the index bits is 0. How about k-way? Well, k-way in this architecture, what we have is we have we have we have in every set we have 2 blocks. In every set we have 2 blocks. 2 blocks. So you have in this cache you have set 0 where set 0 has 2 blocks, set 1 where set 1 has 2 blocks, set 2 where set 2 has 2 blocks, and set 3 where set 3 has 2 blocks. And therefore, in this type of cache, what we can say is that How many? Well, we know that we have the number of blocks in the cache did not change. It's 8. What's the set size? Well, the set size is the K itself. So we have 2 blocks per set. And therefore, what is number of sets? Well, I have in the cache 8 blocks, and I have in each set 2 blocks, which means I have 4 sets, and that's exactly what I have. 1, 2, 3, 4 sets. Okay, so now what is the number of bits that I have? Number of bits that I have. Well, the number of bits for the index, it is log of 2 for 4, which means I need 2 bits for the index. Okay, great. So now let's see for every policy, what is the distribution of the address? So I need some space here. So let me give myself here a space. Okay, all right. So in terms of the address distribution for the direct, so the address distribution or the bits, we know that the least 4 bits are for these 4 bits here. These are block offset. Okay, and we know that the index, I computed, it needs what? Index needs 3 bits. And how about the tag? Well, the tag will use the remaining 25 bits. Okay, how about fully associative? Well, we know the block offset doesn't change. 4 bits for block offset. I'm going to use abbreviation here, block offset. Okay, how about an index? No bits for the index. So the remaining, okay, I need more space here. I kind of deprived myself from a space here. See if I can draw this a better way. Okay, so here, this is block offset. I have 4 bits, and the remaining 28 bits are the tag. No index bits. No index bits, because I have just one set. How about the K-way? Okay, how about the K-way? So the K-way has the following distribution. Oops. Okay, so I have here 4 bits block offset. Okay, and the index. How many bits? 2 bits. 2 bits, and then the remaining 26 bits are tagged. Why I say remaining? Because I know this address is how many bits in total? 32. So I know how to get always the block offset. I know how to get the index. Whatever remains in terms of bits, it should be for the tag. So this is the distribution for the addresses for the direct, for the K-way, which is 2-way in this case, and for the fully associative cache. And you can see in your notes here, I have given some of the rules that you could use. So this is the address here. Just to recap, the address consists of block offset. Okay. So let me use. Sorry. Let's use a highlighter here. So the address consists of block offset, and the remaining we call it block address. And the block address can be partitioned into index and tag. Index, tag, and block. And the block offset, you can think of it word offset and byte offset, but not used very commonly. So the block offset is okay. So number of bits in the blocks, we take the log 2 of 16. In our last example, the block size was 16 bytes, and that gave me 4 bits for the block offset. And these are the block bits. Okay. And the blocks in the cache, in my last example, we said what? We said the cache is 128 bytes, and every block size was, I guess we said what it was. We said it was. Let me just look at my notes here. It should be 16. We said that everyone is 16 bytes, so that gave me 8 blocks. 8 blocks. Okay, in my last example. So sets in the cache is equal to number of blocks, which is 8 divided by the set size. Well, the set size varies based on the policy. Direct set size equals 1. Fully set size equals number of block. K-way set size equal K. So 2-way 2, 4-way 4. And the number of bits for the index is log of the number of sets. Okay, and whatever remaining bits from the address after the index and the block offset is the tag bits. Okay, let's take a look here about this cache example here. He says we have a cache in a direct map, okay, which means what? Set size is what? Set size equals, okay, okay, set size equals 1 block per set. Okay, it has 64 data, so that's the size of the cache. Each block contains 32 bytes. So number of blocks in the cache, you divide the cache size over the size of the block, you get 2048 blocks. Okay, and in this, the address, of course, he's assumed that you have 32-bit address. This is the MIPS address, and he wants me to find out the tag, the index, and the block offset in these address fields. Well, since the block offset has 32 bytes, okay, so this is my address, okay. Since I have 32 bytes, then I would say that we need a log of 32 to the base of 2, which means 5 bits. So it means the block offset we need 5 bits. Okay, and that's what he showed me right here. Now, how many blocks in the cache I have? Well, 64K, this is the K here, divide by 32, that gives me 2048 blocks in the cache. Okay, so how many sets I have? Well, since it's a direct, we know, and the set size equal 1, the number of sets equals number of blocks. Okay, with number of sets equal number of blocks, to find out how many bits of index bits, I take log of 2 to this number, I get 11 bits. Okay, so 11 bits. So this is here the index 11 bits, and whatever remaining in terms of bits is the tag. Okay, as what we have done in the previous example. Here he is doing the same example, but instead of direct, it's two-way. Number of bits and block offset does not change, but number of cache blocks in the cache doesn't change, but number of cells change, because there we divided 2048 by 1, right? But since now 4-way, then the set size equals what? Equals K, and in this case, K equals what? It is equals 4. Okay, so number of sets equal 2048 blocks divided by 4, which is 4, it is the set size. We get 512 sets. Okay, so number of bits, it is the log of 2 of this number, and I get 9 bits in the index. And therefore, if you look at our address, we have the block offset 5 bits, and we have the index 9 bits, okay, and the remaining 18 bits are what? Those are the tag. Okay, all right. So you see how we partition these bits based on the cache policy. Now, in your textbook, he doesn't use the log of 2 and distribution of bits. He uses the modulo. And to be honest, I don't like this method, but feel free to use whatever method makes you comfortable. The formulas that I provided, or the modulo operation that is being used in your textbook, and both are good anyways. Okay, and with this, I'm going to stop here, because we'll talk about the tags and valid bits in the next lecture. Thank you very much.